The cosmos is a puzzle with missing pieces. We are surrounded by cosmic phenomena that science simply cannot explain. This is a journey through 25 of the universe's greatest unsolved mysteries. You will witness everything from strange signals heard only once to invisible forces tearing the fabric of reality apart. We will explore why a star flickers like a broken street lamp and what monstrous gravity is pulling our entire galaxy into the void. By the end, you will see the universe not as a quiet void, but as a chamber of profound and active enigmas. What does it feel like to stand before a mystery that defies all logic? The first mystery arrives not as a slow reveal, but as a single, deafening shout from the void. In the summer of 1977, a radio telescope known as Big Ear at Ohio State University was silently sweeping the sky, listening for whispers from the cosmos. Its job was to record the constant hiss of cosmic static, a background noise scientists hoped might one day be punctuated by something meaningful. On August 15th, it found it. A computer printout fed by the telescope's data began to show a signal. It wasn't a whisper, it was a roar. The signal was 30 times louder than the background noise of space, and it lasted for a full 72 seconds, exactly the length of time the Big Ear telescope could focus on a single point in the sky as the Earth rotated. This wasn't random static, it was focused, powerful, and it occurred at the precise frequency of 1420 MHz, a frequency scientists had long theorized would be a logical choice for interstellar communication because it's a quiet band, naturally protected by the hydrogen that fills the universe. An astronomer named Jerry Amon was reviewing the data days later. He saw the alphanumeric code representing the signal's intensity, circled it, and in the margin wrote one simple, stunned word. Wow! That single word gave the signal its famous name. The WOW signal was everything researchers had hoped to find. It was narrowband, meaning it came from a specific, engineered source, not a natural cosmic event like a star. It rose and fell in intensity perfectly, matching the telescope's listening window. It was, by every technical measure, the textbook signature of an artificial transmission from beyond our solar system. And then it vanished. For decades, astronomers have pointed every available dish at that same patch of sky near the constellation Sagittarius. They have listened for a repeat, a follow-up, anything. The silence has been absolute. The signal never returned. This profound silence is what deepens the mystery. If it was a deliberate beacon, why was it only broadcast once? Explanations have been proposed and fiercely debated. One theory suggested it was a reflection from a passing comet, but that was later challenged and largely dismissed, as comets don't emit strong, narrowband radio waves. Others propose it was a military transmission or a satellite glitch, yet no known human technology at the time matches its unique profile. So we are left with the haunting possibility that, for one brief window in 1977, we heard a cosmic shout. A shout that may have been a one-time accident, a fragment of some distant technology we cannot comprehend, or perhaps a deliberate message that arrived, delivered its unknown meaning, and then ceased forever. The WOW signal stands as a solitary piece of graffiti on the wall of the universe, a single, brilliant question mark etched in radio waves, asking us if we were ever really alone. That solitary shout from the cosmos hints at something we cannot see, but the next mystery is a deafening silence that fills the entire universe. It is not a signal, but an absence, a ghost that holds the cosmos together with invisible hands. This is the enigma of dark matter. Unlike the WOW signal, dark matter is not a single, fleeting event. It is a pervasive, fundamental flaw in our understanding of reality, woven into the very fabric of every galaxy. The story of its discovery begins not with a flash, but with a slow, meticulous realization that the universe was not adding up. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. She expected them to behave like our solar system, where planets closer to the Sun orbit much faster than those farther out. The Sun's gravity weakens with distance, so outer planets like Neptune crawl along their path. Rubin measured the speeds of stars at the edges of distant galaxies, expecting them to be sluggish. What she found was astonishing. Stars on the outer fringes were racing around just as fast as those near the bright galactic center. This was impossible. There simply was not enough visible mass, not enough stars and gas in the glowing center to generate the gravity needed to whip those far-out stars at such tremendous speeds. The only logical conclusion was that something else was there, something invisible, providing an immense extra gravitational pull. This invisible substance forms a vast spherical halo around each galaxy, a ghostly scaffold that holds the speeding stars in place. The evidence for this phantom mass only grew stronger. Look at colossal clusters of galaxies colliding in deep space. Telescopes can see the hot gas from these collisions glowing in X-rays, slowed and tangled by the impact. But careful measurements show that the immense gravity bending light from objects behind these clusters, an effect called gravitational lensing, is not centered on the visible gas or stars. It is offset, as if the true source of gravity, the bulk of the mass, has simply passed right through the collision unscathed. This ghostly mass, unaffected by the cosmic wreck, is dark matter. We see its signature everywhere, even etched into the oldest light in the universe, the cosmic microwave background, the afterglow of the Big Bang. The patterns in that ancient light tell us that dark matter makes up roughly 27% of everything in the cosmos. All the stars, planets, nebulae, and galaxies we see and love account for less than 5%. Yet after decades of searching, we have no idea what it is. It does not emit, absorb, or reflect light. It does not interact with the electromagnetic force at all. It only seems to communicate through gravity. Scientists have built exquisite experiments deep underground in abandoned mines, shielded from cosmic rays, hoping to catch the faintest tick of a dark matter particle bumping into an atom. They have smashed protons together at nearly the speed of light in giant colliders, searching for new particles in the debris. So far, the detectors remain silent. The colliders show nothing new. We are surrounded by an ocean of this mysterious substance, 5 times more abundant than ordinary matter, feeling its gravitational tide in the motion of every galaxy, and we are utterly blind to its true nature. It is the universe's most dominant material and its greatest secret. But if dark matter is the ghostly skeleton holding galaxies together, then dark energy is the phantom breath inflating the entire cosmos. It is an even more baffling force, one that does not pull things together but pushes them apart with ever-increasing strength. This discovery did not come from a single, dramatic observation, but from a slow, chilling realization that our universe's story had a shocking twist. For most of the 20th century, scientists believed the universe began with the Big Bang and had been expanding ever since. The central question was whether that expansion would eventually slow down, pulled by the collective gravity of all matter, perhaps even reversing into a big crunch. In the 1990s, 2 independent teams of astronomers set out to measure this cosmic slowdown by studying distant stellar explosions called Type 1, a supernova. These supernovae are cosmic standard candles exploding with a known, predictable brightness. By measuring how dim they appear from Earth, scientists can calculate their exact distance. And by analyzing the color of their light stretched by the expansion of space, they can determine how fast the universe was expanding when that light was emitted billions of years ago. The teams expected to see that distant, ancient supernova were closer than their dimness suggested, meaning the universe was expanding faster in the past and has since slowed down. Instead, they found the opposite. The supernova were farther away. The universe's expansion was not slowing at all. It was accelerating. It was as if you threw a ball into the air, and instead of falling back down, it shot away faster and faster into the sky. This result was so shocking, so contrary to all expectations, that the researchers spent years checking and rechecking for errors. There were none. The universe is on a runaway train, and dark energy is the unseen engine. We now understand that dark energy makes up about 68% of the total energy budget of the cosmos. It is not a substance like dark matter, but a property of empty space itself. Think of the vacuum of space not as a true nothing, but as a seething quantum foam, constantly generating and annihilating pairs of virtual particles. This activity gives the vacuum an inherent energy, and according to Einstein's theory of relativity, energy has gravity. But this is a gravity with a negative sign, a repulsive pressure that causes space itself to stretch. The leading candidate for dark energy is Einstein's own cosmological constant, a term he famously inserted into his equations to keep the universe static, later calling it his greatest blunder. Ironically, it may be his greatest prediction, yet the cosmological constant presents a problem of staggering proportions. When physicists calculate the predicted strength of this vacuum energy from quantum theory, the number they get is wrong by a factor of 1 followed by 120 zeros. It is the worst mismatch between theory and observation in the history of science. This means our understanding of the quantum world and the large-scale cosmos are fundamentally incompatible. Dark energy is not just another mystery, it is a direct challenge to the foundations of physics. It dictates the ultimate fate of everything. If it continues to dominate as it does now, the acceleration will increase. In a distant future, galaxies outside our own local group will be pushed away so fast their light will never reach us. The observable universe will shrink to a lonely island of stars in an infinite, expanding blackness. We are living in the last era where the cosmos is still knowable, and the force that is writing this bleak final chapter remains utterly unknown to us. While dark energy writes the universe's distant future, another phenomenon delivers its messages in sudden, violent bursts that illuminate the present. These are fast radio bursts, or FRBs, the cosmos's most powerful and perplexing flashes. They arrive without warning, a blast of radio waves so intense it can outshine an entire galaxy, yet it lasts for less than the blink of an eye. The first was discovered in 2007, not in real time, but by an astronomer named Duncan Lorimer sifting through old archival data from a radio telescope in Australia. The recording showed a single, spectacular spike of energy that had erupted 6 years earlier, a 5-millisecond burst that had traveled across billions of light years. For years, it was considered a possible fluke, a one-off anomaly. Then astronomers found another and another. Today, we detect them almost daily. The power behind these flashes is almost incomprehensible. In that thousandth of a second, an FRB can release as much energy as our sun puts out over 80 years. Imagine focusing the entire output of hundreds of millions of stars into a single, ultra-brief pulse and firing it across the universe. That is the raw, explosive force we are detecting. What makes them even stranger is their behavior. The vast majority are one-time events, a cosmic shout that is never heard again. But a handful, a precious few, are repeaters. They flash once, go silent for days or months, and then flash again from the exact same point in the sky. This repetition is a crucial clue, ruling out catastrophic, one-time events like the collision and destruction of 2 neutron stars. The hunt for their origin has become one of astronomy's greatest detective stories. The prime suspect today is a type of stellar corpse called a magnetar. These are neutron stars with magnetic fields so powerful they could erase a credit card from halfway to the moon. Theorists suggest that starquakes on a magnetar's surface, or sudden magnetic reconnections similar to solar flares but infinitely more powerful, could generate these colossal radio bursts. In 2020, a magnetar within our own Milky Way galaxy emitted a radio burst that, while much weaker than the extragalactic FRBS, confirmed that these objects are indeed capable of such eruptions. Yet the mystery is far from solved. Some repeating bursts show patterns that are difficult to explain with simple starquakes, and the sheer energy of the most distant bursts pushes the limits of what we believe even a magnetar can do. This has led to more speculative ideas, including the possibility of advanced technology. Could these be power beams for alien light sails, or perhaps the leakage from unimaginably powerful transmitters? While astronomers consider this the least likely explanation, the sheer extremity of FRBS means no idea is entirely off the table. The real breakthrough has been in localization. By using networks of telescopes across the globe, scientists have managed to trace several bursts, including some repeaters, back to their home galaxies. They come from vastly different environments, from tiny, turbulent dwarf galaxies to the spiral arms of larger ones. This diversity tells us that whatever engine produces these bursts, it can operate in many cosmic neighborhoods. Each new detection is a piece of a puzzle we are still assembling, a fleeting signal from a universe that seems to specialize in sudden, brilliant, and utterly mysterious violence. The universe specializes in sudden, brilliant violence, but its strangest mysteries are often the slow, patient ones. In the constellation Cygnus, there is a star that does not explode but simply winks. Its name is Tabby's star, officially catalogued as KIC 8462852, and it behaves like nothing else we have ever seen. The discovery did not come from a professional astronomer in a control room, but from the collective curiosity of the internet. As part of the Planet Hunters project, ordinary people were sifting through data from NASA's Kepler Space Telescope, looking for the telltale, periodic dips in starlight caused by orbiting planets. What they found in this star's data was not a tidy, repeating pattern. It was chaos. The light from Tabby's star drops by staggering amounts, sometimes more than 22%, and it does so in irregular, jagged shapes that last for days or weeks. A planet, even a giant one, would block at most 1% of a star's light in a smooth, symmetrical curve. This was something else entirely. It was as if enormous, misshapen objects of unknown origin were drifting in front of the star, blocking its light in a bizarre and unpredictable dance. The scientific community scrambled for explanations. The first, most natural idea was a colossal swarm of comets, thousands of them, breaking apart and creating vast clouds of dust and debris. But to cause dips this deep, the swarm would have to be impossibly large and dense, a scenario that pushes the limits of what we think a solar system can produce. Others suggested a recent planetary collision, leaving a field of shattered rock and glowing vapor drifting across our line of sight. Or perhaps it was not the star itself, but a vast cloud of interstellar dust drifting between us and it, a cosmic fog bank. Each theory had serious flaws. Natural dust should glow in infrared light, and Tabby's star shows no such excess glow. A collision would be a one-time event, yet the dips have been observed happening for years. This is where the most famous and most speculative hypothesis entered the conversation. In the 1960s, physicist Freeman Dyson proposed that a sufficiently advanced civilization would eventually need to capture nearly all the energy from its star. They might build a vast swarm of orbiting collectors, a megastructure often called a Dyson sphere. Such a structure, under construction and incomplete, would block starlight in exactly the kind of large, irregular, and non-repeating pattern we see from Tabby's star. The idea captured the public imagination instantly. A star being enclosed by an alien megaproject was a breathtaking possibility. Scientists, however, remain deeply skeptical, and for good reason. Extraordinary claims require extraordinary evidence, and a Dyson sphere is the most extraordinary claim of all. The scientific method demands we exhaust every possible natural explanation before leaping to a technological one. Follow-up observations have provided clues that point away from solid megastructures. Detailed studies of the star's light show that different colors are dimmed by different amounts, a strong signature of fine dust, not solid panels or spacecraft. The most likely culprit now seems to be an immense, evolving cloud of exceptionally fine dust particles, perhaps from a disintegrating moon or a captured interstellar object orbiting in a strange, clumpy ring. Yet even this natural explanation feels unsatisfying because the dust itself must come from somewhere, and its behavior remains uniquely odd. Tabby's star endures not as proof of aliens, but as a masterclass in cosmic curiosity. It is a reminder that when we look closely enough, the universe still has the capacity to shock us with pure, unadulterated weirdness. It forces astronomers to question every assumption about how solar systems form and evolve. The true answer may be a natural process we have simply never witnessed before, something stranger than our wildest fiction, and that in itself is a profound kind of discovery. The strange, patient mysteries of a single star are mirrored by a slow, subtle drift in our own cosmic neighborhood. While Tabby's star winks from hundreds of light years away, a much closer puzzle was unfolding silently in the deep cold beyond Pluto. The Pioneer 10 and Pioneer 11 spacecraft, humanity's first emissaries to the outer planets and beyond, carried with them a secret they were not designed to reveal. After their triumphant flybys of Jupiter and Saturn, these robotic pioneers continued on trajectories that would carry them out of the solar system forever. Scientists, using exquisitely precise Doppler tracking, monitored their radio signals to plot their exact positions across billions of miles. Over time, a tiny, nagging discrepancy emerged. Both spacecraft were experiencing a minute, constant acceleration back toward the Sun. It was an almost imperceptible pull, a drift so small it amounted to less than a 10/1000th of the gravity we feel on Earth. But in the pristine silence of interplanetary space, where the laws of physics are expected to hold with perfect clarity, this anomaly was a glaring red flag. For decades, this pioneer anomaly represented a profound mystery. Could it be a sign of unknown physics, perhaps a flaw in our understanding of gravity itself at the largest scales, or the gravitational pull of unseen, dark matter concentrated in our solar system? The idea that our most fundamental theories might be cracking under the strain of such a tiny measurement captivated and troubled physicists. The quest for an answer became a grand detective story, involving teams sifting through decades-old engineering documents, reconstructing the spacecraft's designs from blueprints, and modeling every conceivable force. The leading explanation that finally emerged was both elegant and humbling. It pointed not to new physics, but to the simple, overlooked physics of heat. The Pioneer probes were powered by radioactive plutonium, whose decay generated both electricity and waste heat. This heat radiated away from the spacecraft's surfaces. Crucially, the main dish antenna, pointed steadfastly back at Earth for communication, also acted as a reflector. More heat was radiating from the back of the spacecraft, pushing forward, than from the front, which was shielded by the antenna. This anisotropic, or directionally uneven, thermal radiation created a tiny but constant photon pressure, a gentle push back toward the Sun that perfectly matched the observed anomaly. It was the spacecraft's own warmth slowly breaking their escape. While this thermal explanation is now widely accepted, some researchers argue that a tiny fraction of the anomaly remains unaccounted for, a ghost in the data that refuses to vanish completely. Whether fully solved or not, the Pioneer anomaly serves as a powerful lesson. It reminds us that the universe's greatest puzzles are not always found in distant galaxies or in catastrophic explosions. Sometimes they are hiding in plain sight, in the meticulous tracking of a human-made object drifting through the silent dark, revealing that even in our own celestial backyard, we must check our assumptions with relentless care. That gentle push from a spacecraft's own warmth was a subtle clue. But sometimes the universe's mysteries appear not in the silent drift, but in the high-speed ballet of a planetary flyby. When we send our robotic explorers across the solar system, we often use the planets themselves as gravitational catapults. A spacecraft swings close to a world like Earth, steals a tiny fraction of its orbital momentum, and is flung toward its destination at greater speed. We calculate these slingshot maneuvers with phenomenal precision. A mistake of even a millimeter per second at Earth can mean missing Mars by hundreds of miles. Yet sometimes, against all expectation, our measurements are wrong. This is the flyby anomaly. It was first noticed with the Galileo spacecraft in 1990. As it whipped past Earth to gain momentum for its journey to Jupiter, tracking stations found its final speed was about 4 millimeters per second faster than our best models predicted. 4 millimeters per second is less than a slow walking pace. In the vastness of space, it seems trivial, but in the world of orbital mechanics where predictions are exact, it was a glaring error. The anomaly popped up again and then again. The near-Shoemaker probe headed to an asteroid saw a discrepancy of over 13 millimeters per second after its Earth flyby. The Rosetta Comet chaser on its long voyage showed a smaller but still significant shift. Each event was a tiny, persistent whisper that our understanding of gravity during these complex maneuvers was incomplete. Scientists have combed through every possible mundane explanation. Could it be the drag from Earth's outer atmosphere, even at high altitude? Could it be the pressure of radiation from the sun or subtle tidal forces from the moon? Perhaps the way Earth's rotation warps spacetime itself, an effect called frame dragging, needed more careful accounting. Yet even after incorporating our most sophisticated models of the atmosphere and relativity, the tiny speed differences stubbornly remain. This has led to more radical proposals. Some physicists suggest it could be a sign of modified gravity, a hint that Einstein's theory, while overwhelmingly successful, might need a tiny adjustment under certain conditions. Others have pondered whether the anomaly could be a clue to unseen dimensions, as proposed in some string theory models, where gravity might leak slightly into other realms, affecting spacecraft in ways we cannot yet predict. While none of these exotic ideas are mainstream, their very consideration highlights the depth of the puzzle. The flyby anomaly is a testament to both our mastery and our ignorance. We can navigate a tiny probe across billions of miles to rendezvous with a comet, but we cannot fully account for a speed change no greater than a drifting snowflake. It is a reminder that our maps of reality, though incredibly detailed, may still have faint, unexplored contours waiting to be revealed by the silent passage of a machine through the night. This relentless pull we measure on our spacecraft is a faint echo of a far greater force, one that grips our entire galaxy and everything around it. Our Milky Way is not drifting aimlessly through the cosmos. It is racing along with our entire local group of galaxies at an astonishing speed of over 2 million kilometers per hour toward a specific point in the deep sky, toward the constellation Centaurus. This mysterious destination is known as the Great Attractor. Imagine the gravitational pull of 1 billion suns, a force so colossal it can redirect the motion of galaxies as if they were leaves in a stream. That is the scale of the anomaly we are caught within. For a long time, its nature was completely obscured because it lies directly behind the plane of our own Milky Way, a region astronomers call the zone of avoidance. Here, thick clouds of interstellar dust and the dense glitter of countless stars create a visual wall, blocking our optical view of the universe beyond. It was like trying to see a distant city through a blinding fog bank. We could not see the Great Attractor, but we could feel its irresistible tug. Scientists mapped the motions of thousands of galaxies in our vicinity, and every single stream of motion pointed toward that one hidden spot, revealing a gravitational deficit of staggering proportions. Something over there was pulling us in, As observational technology advanced, particularly with X-ray and radio telescopes that can peer through the cosmic dust, the picture began to clarify. We discovered that at the heart of this mystery lies a massive concentration of matter known as the Norma cluster, an enormous gathering of galaxies bound together by gravity. This cluster is immense, but it soon became clear that even the Norma cluster was not the full story. It is merely the brightest knot in a much larger cosmic web. Our entire local group, the Norma cluster, and countless other galaxies are all part of an unfathomably vast structure now called the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is a filamentary network of galaxies spanning over 500 million light-years, all flowing toward a common gravitational center, a valley of cosmic density. The Great Attractor appears to be the core of this supercluster, yet here is the lingering mystery, even with this grand discovery. When astronomers add up all the visible mass in the Norma cluster and the surrounding Laniakea region, it still does not fully account for the immense velocity at which we are being pulled. There seems to be even more mass, more hidden gravitational source, lying behind the Great Attractor itself, pulling on it and us in a cosmic chain. Some researchers point to an even more colossal structure in that direction, known as the Vela supercluster, only recently confirmed, which may be contributing to this grand flow. So the search continues. The Great Attractor is no longer a single, unseen monster in the dark, but rather a signpost, a gravitational landmark pointing toward the large-scale architecture of the universe itself. It teaches us that we are part of a cosmic current, a river of galaxies flowing down slopes of gravity carved by both the visible universe and the profound, unseen depths of dark matter. Our journey toward it is a journey into the heart of the cosmic web, and we are still discovering what lies at its center. This grand flow of galaxies is part of a universe we believe to be fundamentally fair and even-handed. There is a cornerstone principle in cosmology, a rule so basic it underpins everything we know. It is called the cosmological principle, and it states that on the largest scales, the universe is isotropic and homogeneous. In simpler terms, it should look the same in every direction, with no special place and no preferred axis. It is the foundation upon which we built our model of the Big Bang and cosmic expansion. But what if that foundation has a crack? What if the oldest picture we have of the universe shows a ghostly direction, a cosmic bias written into the fabric of reality itself? This is the unsettling mystery known as the axis of evil. Our deepest glimpse into the infant universe comes from the cosmic microwave background, the CMB. This is the faint afterglow of the Big Bang, a snapshot of the cosmos when it was just 380,000 years old, a glowing fog of hot plasma that has since cooled and stretched into a bath of microwave radiation that permeates all of space. For decades, satellites like WMAP and Planck have mapped this ancient light in exquisite detail. The map shows a nearly uniform temperature, about 2.7 degrees above absolute zero, dotted with tiny fluctuations, hot and cold spots that represent the seeds of all future structure, the galaxies and clusters we see today. According to our theories, these fluctuations should be random. They should be scattered across the sky like a cosmic fingerprint with no pattern or alignment. They should obey the cosmological principle perfectly. The data, however, tells a different and deeply puzzling story. When scientists analyze the patterns in the CMB, they find hints of a strange correlation. Certain large-scale features, the alignments of the hot and cold spots, seem to be oriented along a particular line or axis in space. It is as if the entire infant universe had a slight tilt, a preferred direction. This apparent alignment has been nicknamed the axis of evil, a name that reflects just how troubling it is to cosmologists. If real, it suggests the universe has a handedness, a lopsidedness that violates our most cherished assumption of cosmic fairness. The implications are profound. A genuine axis would mean the universe is not isotropic. it would imply there is a special direction, which in turn could mean there is a special place. This would force us to reconsider everything from the inflationary epoch, the period of hyper-expansion just after the Big Bang, to the very nature of the cosmos before it began. Could this axis be a fossil, an imprint of some structure that existed before the Big Bang? Or is it a sign that the process of inflation, which was meant to smooth the universe into uniformity, did not operate quite the way we think? Perhaps it stretched space in a slightly uneven way, leaving behind this eerie signature. Many scientists have worked tirelessly to explain it away as a statistical fluke or an artifact of our own observation. Could it be contamination from our solar system's motion, or dust within our own Milky Way galaxy? The Planck satellite team conducted exhaustive checks, and while they could account for some of the anomaly, a strange sense of alignment stubbornly remained at the largest scales. It refuses to vanish. This leaves cosmology in an uncomfortable position. The axis of evil may be a phantom in the data, a trick of chance that will disappear with more precise measurements. But if it persists, it is a direct challenge to the cosmological principle, a whisper from the dawn of time that the universe might be fundamentally stranger and less uniform than we ever dared to imagine. If the cosmos has a hidden axis, then its chemical recipe book also contains a glaring misprint. The very first elements were forged in the universe's explosive birth, a process we think we understand with remarkable precision. Yet one ingredient, a simple metal found in your phone battery, refuses to follow the cosmic script. This is the lithium problem, and it strikes at the heart of our origin story. In the first 3 minutes after the Big Bang, the universe was a seething nuclear furnace. Protons and neutrons, freshly formed, slammed together in the unimaginable heat and density. This brief epoch, known as Big Bang nucleosynthesis, cooked up the primordial soup of light elements, vast amounts of hydrogen, a good portion of helium, and trace quantities of deuterium and lithium. The physics governing this process is based on well-tested nuclear cross-sections and the known expansion rate of the early universe. Scientists can plug these numbers into their models and predict with great confidence exactly how much of each element should have been created. For deuterium and helium, the predictions match the amounts we observe in ancient gas clouds almost perfectly. It is a triumphant confirmation of the Big Bang model. But lithium breaks this perfect record, specifically the isotope lithium-7. Our theoretical calculations tell us that for every 10 billion hydrogen atoms in the primordial universe, there should be about 5 atoms of lithium-7. When astronomers point their telescopes at the oldest stars in the Milky Way, stars that formed from nearly pure primordial gas, they measure a number 3 times smaller. These ancient stellar time capsules contain only about 1 lithium atom for every 10 billion hydrogen atoms, 1/3 of the expected amount. This is not a small discrepancy, it is a fundamental mismatch. Our universe's recipe book is wrong, and we have been serving the wrong amount of this cosmic ingredient for over 13 billion years. The hunt for the missing lithium has become a major puzzle in cosmology and astrophysics. Where did it go, or was it never made in the amounts we think? Scientists have pursued several compelling yet unresolved paths. The first possibility involves the nuclear physics of the infant cosmos itself. Could there be unknown nuclear reactions, pathways we haven't considered, that destroyed lithium-7 as quickly as it formed in those first fiery minutes? Perhaps our understanding of the conditions during nucleosynthesis is subtly incomplete. The second path looks to the stars themselves. Could these ancient stellar furnaces have somehow destroyed their primordial lithium over billions of years? Stars mix and burn material in their cores, and certain types of stellar rotation or internal currents might drag surface lithium down into hot interior regions where it is fused into heavier elements. If this process is more efficient than we thought, it could explain the low observed levels, yet finding evidence for this in the most pristine, unchanged stars remains difficult. The most radical path points to entirely new physics. Could exotic particles from the dark sector have been present in those first minutes? Certain theoretical particles, like decaying supersymmetric particles, could have altered the nuclear reaction rates or changed the neutron-to-proton ratio, skewing the entire lithium yield. This solution is tantalizing because it connects a problem in nuclear astrophysics to the greater mysteries of dark matter and particle physics beyond the standard model. Each proposed solution has its challenges, and none have yet provided a definitive answer. The lithium problem endures as a quiet but profound crisis. It tells us that our detailed understanding of the universe's first moments, a story we tell with such authority, still has a crucial page missing. The oldest stars in the sky are holding a secret, and until we solve it, we cannot truly claim to know the recipe for our own existence. The recipe for our own existence may be uncertain, but in the skies of another world, a geometric marvel defies all weather. High above the cloud tops of Saturn at its north pole, a storm rages unlike any other in the solar system. It is not a swirling vortex, but a perfect colossal hexagon. This six-sided jet stream, wider than two Earths placed side by side, is a work of celestial geometry so precise it looks engineered. The Voyager probes first glimpsed its shadowy outline in the 1980s, a fleeting mystery in grainy images. Decades later, NASA Cassini spacecraft arrived for a long-term study, and its cameras revealed the hexagon in breathtaking, terrifying detail. It is a wall of clouds, a racing river of wind forming the edges of a polygon, with each side stretching over 8,000 miles. Inside its boundaries, the atmosphere churns, but the shape itself is immaculate, a honeycomb cell stamped onto a gas giant. What makes this structure truly mind-bending is its endurance. Cassini observed it for over 13 years, watching as Saturn's seasons slowly changed from winter to summer at the North Pole. Through that entire transition, as sunlight returned to the frozen pole, the hexagon remained. It has persisted for at least 40 Earth years and likely much longer, a permanent feature rotating in lockstep with the planet's deep interior. This stability is the core of the puzzle. On Earth, our weather is chaotic and transient. Even Jupiter's great red spot, while centuries old, is a slowly shrinking oval. Saturn's hexagon is a rigid, geometric storm that has outlasted generations of human observation. How can an atmosphere, a fluid system of gas, hold such a sharp, angular shape for so long? Scientists have turned to laboratory experiments for clues. In tanks of spinning water, researchers can create similar polygonal shapes, including hexagons, by varying the rotation speed and the flow of the fluid. These experiments show that under certain conditions, instabilities between jet streams of different speeds can naturally produce straight edges and corners. This suggests the hexagon is a standing wave pattern, a stable oscillation in Saturn's fast-moving polar atmosphere. But scaling this from a water tank to a planetary behemoth is the staggering leap. The forces involved are almost unimaginable. The winds along those hexagonal edges scream at speeds over 300 miles per hour. To maintain those razor-sharp angles across a structure of continental scale, and to do it with such clockwork stability across decades, requires a perfect planetary-scale balance of forces we do not fully understand. It hints at deep, hidden layers of Saturn's atmospheric dynamics, a complex dance between the upper clouds we see and the churning metallic hydrogen far below that generates the planet's powerful magnetic field. The hexagon is more than a beautiful curiosity, it is a natural laboratory. Its very existence challenges our models of fluid dynamics and planetary meteorology, proving that in the right conditions, nature can produce geometry of a precision that rivals our own most careful designs. It is a lesson written in ammonia clouds, telling us that even the most familiar physical laws can yield utterly alien artistry when played out on a cosmic stage. That alien artistry on Saturn is a fleeting wonder, but in the depths of space, another geometric masterpiece has been sculpted to last for millennia. Gaze upon the Red Rectangle Nebula, a cosmic structure so precise it seems drawn with a ruler and compass. Located about 2,300 light-years away in the constellation Monoceros, this is not a typical, chaotic cloud of stellar death. It is a breathtaking exception. At its heart lies a close binary star system, HD 44179, where one star has exhausted its fuel and is shedding its outer layers. In most cases, this creates a spherical planetary nebula, a glowing bubble of gas. The Red Rectangle is something else entirely. Through the lens of the Hubble Space Telescope, it reveals itself as a stunning, symmetrical form. Two opposing cones of glowing gas extend from the central stars, forming a distinct X shape. Connecting these cones are concentric rungs of dust, creating the illusion of a celestial ladder or a three-dimensional rectangular frame viewed from the corner. The entire structure glows with a deep, rusty red hue, a color born not from fire but from complex chemistry. The profound mystery here is one of order versus chaos. How does a dying star, in its final turbulent throes, produce such architectural perfection? The leading theory points to an extremely dense, donut-shaped disk of dust that tightly orbits the binary stars. Imagine a spinning top with a thick belt around its middle. As the dying star expels gas, this outflow is funneled into two narrow jets above and below the disk, like water squeezed from a spray bottle, creating the bipolar cones. The concentric rungs are thought to be shock waves, rhythmic pulsations in the outflow that create ripples in the surrounding dust, much like sound waves forming visible patterns in a vibrating plate of sand. Yet this explanation, while elegant, feels incomplete. The symmetry is too perfect, the rungs too evenly spaced. The physics that dictates the exact spacing and stability of these structures over such vast scales remains an active puzzle. Adding to the enigma is the nebula's strange composition. Its distinctive red glow comes from a class of organic molecules known as polycyclic aromatic hydrocarbons, or PAHs. These are complex carbon-based compounds, essentially flakes of soot, that fluoresce under the intense ultraviolet light from the central stars. They are found throughout interstellar space, but in the Red Rectangle, they appear in unusual abundance and structure. Some scientists speculate that the unique environment within the nebula's dense dust disks might be a cosmic factory, building these probiotic molecules, the very building blocks of life, with extraordinary efficiency. The Red Rectangle, therefore, is more than a beautiful oddity. It is a natural laboratory where the forces of geometry, stellar death, and organic chemistry collide. It asks us a fundamental question: are the seeds of life, those carbon-rich compounds, forged in the precise, geometric crucibles of dying stars? This crimson rectangle in the sky offers no final answer, only a silent, stunning testament to the universe's capacity for both exactitude and mystery. The universe's artistic geometry is born from forces of immense violence, and nothing embodies that raw, explosive power more than a single subatomic bullet screaming across the cosmos. These are ultra-high-energy cosmic rays, and they carry a punch that defies belief. They are not rays of light, but particles, usually single protons, traveling at a fraction below the speed of light. When one of these microscopic projectiles slams into Earth's upper atmosphere, it unleashes a catastrophic cascade of secondary particles, a sprawling air shower that can spread over dozens of square kilometers. The energy packed into that one tiny proton is staggering. The most powerful ones detected carry over 50 joules of energy. That may not sound like much, but consider the scale. It is a subatomic particle, a billionth of a meter across, hitting with the kinetic energy of a professionally thrown baseball. It is millions of times more energetic than anything we can produce in our most powerful particle colliders, like the Large Hadron Collider. These particles are nature's own particle accelerators, operating on a scale we cannot yet replicate. Their existence is not just impressive, it is theoretically baffling. The universe, far from empty, is filled with the faint afterglow of the Big Bang, the cosmic microwave background. This sea of low-energy photons acts like a cosmic fog for these ultra-fast protons. Over immense intergalactic distances, a proton traveling at such insane speeds should constantly collide with these background photons. Each collision saps its energy, a process physicists call the Greisen-Zatsepin-Kuzmin, or GZK, cutoff. It acts like a speed limit for cosmic rays across the universe. This means any ultra-high energy cosmic ray we detect must have come from a relatively nearby source within our cosmic neighborhood, within about 300 million light-years or so. It cannot have traveled from the distant early universe, so the mystery sharpens. We know these unimaginable particle accelerators must be relatively close by on the grand scale of the cosmos. Yet when we trace the incoming direction of these rare events back into the sky, we find no obvious, brilliant source staring back at us. For decades, massive observatories like the Pierre Auger Array in Argentina have been hunting for these ghosts. The Auger Array covers an area of 3,000 square kilometers, an expanse the size of Rhode Island, dotted with over 1,600 water tanks that detect the faint flashes of light from air showers, while telescopes watch for the ultraviolet glow they produce in the night sky. It captures these ultra-rare events, perhaps 1 per square kilometer per century. The data has provided clues, but not a definitive answer. The arrival directions of these cosmic rays are not completely random. They show a weak correlation with the locations of nearby active galactic nuclei, supermassive black holes at the hearts of galaxies that are voraciously consuming matter and spewing out jets of radiation. Other suspects include cataclysmic gamma-ray bursts, the explosive deaths of massive stars, or perhaps even more exotic engines like colliding galaxy clusters or magnetars. But the correlation is not perfect. Many cosmic rays seem to come from empty patches of sky, and no single type of source explains all the events. This points to a profound gap in our knowledge. Somewhere in our galactic backyard, there are engines of acceleration so ferocious they can take a single proton and stamp it with more energy than we can ever hope to create. These engines operate by principles we are still piecing together, likely involving shock waves spanning millions of light-years, magnetic fields of incomprehensible strength, or volumes of space where conditions are more extreme than anywhere else we can observe. Each ultra-high-energy cosmic ray that rains down is a messenger from one of these extreme environments, a calling card from a cosmic powerhouse we have yet to fully identify. They remind us that the universe harbors natural accelerators of almost impossible violence operating in the dark, their mechanisms still hidden from our view. These messengers of unimaginable violence arrive from our own cosmic neighborhood, but another puzzle is written into the very history of our own star. Billions of years ago, when life first stirred on Earth, our sun was a fundamentally different star. Nuclear fusion in its core was less efficient, making it only about 70% as bright as it is today. According to every basic climate model we have, that faint young sun should not have provided enough warmth to keep Earth's oceans liquid. Our planet should have been a global ice ball, a frozen snowball hurtling through space, its surface locked in a deep, permanent winter. Yet the geological record tells a completely different and warmer story. Ancient rocks over 3 billion years old show clear evidence of liquid water ripple marks, rounded pebbles, and minerals that can only form in a wet environment. Even more astonishing, the fossilized remains of microbial life appear in rocks from this very era. The Earth was not only unfrozen, it was hospitable. This glaring contradiction between the physics of stars and the geology of our planet is the faint young sun paradox. Solving this paradox means finding a source of extra heat, a planetary blanket that kept the early Earth cozy under a dimmer sun. The leading explanation points to the planet's own atmosphere, which must have been very different from the one we breathe today. scientists propose it was far richer in powerful greenhouse gases like carbon dioxide and methane. A much thicker carbon dioxide atmosphere, perhaps hundreds of times denser than today's, could have trapped enough infrared radiation to offset the solar shortfall. Methane, an even more potent greenhouse gas, likely played a major role, possibly produced in vast quantities by early microbial life itself. This creates a fascinating feedback loop. Life may have helped create the very conditions necessary for its own survival. Other factors could have contributed to this planetary balancing act. The young Earth itself looked different. With fewer continents, the planet's albedo, its reflectivity, would have been lower. Less sunlight would have bounced off a darker, ocean-dominated surface back into space, allowing more heat to be absorbed. Volcanic activity was also more rampant, pumping both heat and gases like carbon dioxide directly into the atmosphere. The puzzle for climatologists is not finding a possible solution, but finding the precise mix. Getting the numbers right is incredibly difficult. Too much greenhouse gas, and you overheat the planet, creating a runaway greenhouse effect like Venus. Too little, and the glaciers advance. The early Earth somehow walked this razor's edge for billions of years. While we have plausible ideas, the faint young sun paradox endures as a profound reminder. It shows that a planet's climate is not a simple dial set by its star. It is an exquisitely complex and finely tuned system, a dance between stellar radiation, atmospheric chemistry, geology, and even biology. Our own world's ability to maintain liquid water across eons under a changing sun hints at a stability that is both miraculous and perhaps extraordinarily rare. That delicate balance of our early climate was maintained here on Earth, but in 2017, a visitor arrived that had never known a sun's warmth at all. It was the first tourist from another star system ever spotted passing through our cosmic neighborhood, and it defied every expectation. Astronomers at the Pan-STARRS telescope in Hawaii detected a faint point of light moving at blistering speed, on a trajectory so extreme it could only have come from the depths of interstellar space. They named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. This was no ordinary asteroid or comet from our own solar system. It was a relic from a star system light years away, and its brief flyby left behind a trail of profound questions. The data revealed an object of bizarre and unprecedented characteristics. By carefully measuring how its brightness changed over time, astronomers inferred its shape. It was not round. The light curve suggested an extremely elongated object, tumbling end over end through space. The best fit was a pancake or cigar shape, with a length perhaps 10 times greater than its width. Nothing in our solar system looks quite like that. Even stranger was what it lacked. As it swung around the sun, coming within a quarter of the Earth-Sun distance, most scientists expected it to behave like a comet. The intense solar heat should have vaporized ices on its surface, releasing gas and dust to form a visible fuzzy coma and tail. Oumuamua showed no such activity. Its surface appeared dark and inert like that of an asteroid. Then came the true head-scratcher. As it sped away from the sun, detailed tracking showed its path could not be explained by gravity alone. There was an extra push, a slight but undeniable non-gravitational acceleration. For comets, this is commonplace. Jets of outgassing act like weak rocket engines, nudging the object off a purely gravitational path. But Oumuamua had shown no coma, no dust, no visible gas. So what was pushing it? The scientific community scrambled for natural explanations. One compelling idea proposed that Oumuamua was made largely of hydrogen ice. Solid hydrogen is invisible to our telescopes when it sublimates, and it could provide just enough jet-like thrust to explain the acceleration without a visible tail. Another theory suggested it was a fragment of a Pluto-like world, a shard of nitrogen ice that eroded away as it traveled. Each natural hypothesis, however, had to stretch known physics to accommodate all of Oumuamua's oddities simultaneously: its shape, its lack of visible outgassing, and its precise acceleration. This opened the door for a far more speculative idea. Harvard astronomer Avi Loeb famously suggested we should consider the possibility that Oumuamua was a piece of alien technology. He proposed it could be a discarded light sail, a thin, manufactured object pushed by the radiation pressure of Starlight, which would account for its flat shape and its non-gravitational boost. This hypothesis ignited a firestorm of debate, both within academia and in the public sphere. For many scientists, it was a leap too far, an argument from ignorance that bypassed the hard work of finding a natural explanation. They argued extraordinary claims require extraordinary evidence, and a weird shape and a slight acceleration did not meet that bar. The debate became less about the object itself and more about the scientific process, how we confront anomalies, and when, if ever, it is appropriate to invoke intelligence as an explanation. Oumuamua is now long gone, vanishing into the dark beyond Neptune, never to be seen again. Its legacy is not an answer but a profound shift in perspective. It proved interstellar objects are not just theoretical, they are passing through our system regularly, and we now have the tools to find them. It forced astronomers to expand their catalogues of what is possible in nature, considering exotic ices and strange formation histories. And it posed a tantalizing, unresolved question. When the next interstellar scout arrives, will its mysteries be easier to solve, or will it be stranger still? Deep within the heart of our own galaxy, a silent, brilliant fog refuses to reveal its source. The center of the Milky Way should be a place of predictable chaos, dominated by the immense gravity of the supermassive black hole Sagittarius, a star, surrounded by ancient stars and the corpses of dead ones. When the Fermi Gamma-ray Space Telescope turned its gaze toward this region, it expected to see gamma rays, the most energetic form of light, sparking from known cosmic engines like pulsars and stellar remnants. Instead, it found something far more puzzling: a mysterious, diffuse glow. This is the galactic center excess, a vast and unexplained sphere of gamma-ray light radiating from the core of our home galaxy. The light itself is not the mystery. Gamma rays are produced by the most violent events in the universe. The mystery is its pattern. The excess forms a remarkably smooth, spherical halo centered on the galactic core, extending for thousands of light years. This smoothness is the critical clue that something strange is at work. Known point sources like pulsars, the rapidly spinning, magnetized cores of dead stars, would create a lumpy, clumpy distribution of light across the sky, not this uniform fog. It is as if you are looking at a city at night expecting to see distinct street lamps and car headlights, but instead you see a pervasive, even glow illuminating everything from a hidden, city-wide source. This peculiar signature is what makes the galactic center excess so thrilling to physicists. One of the most compelling hypotheses points directly to the universe's greatest unknown: dark matter. According to leading theories, dark matter particles could be their own antimatter counterparts. If this is true, then wherever dark matter is densely concentrated, like the core of our galaxy, these particles could occasionally collide and annihilate each other, converting their mass directly into energy and producing a spray of gamma rays. The predicted signal from such annihilations would be a smooth, spherical glow, exactly matching what Fermi sees. For a time, this dark matter interpretation seemed like a potential breakthrough, a way to finally see the invisible substance that shapes the cosmos. Yet science demands we rule out all mundane possibilities first, and astronomers have proposed several. The leading alternative suggests the glow could come from a vast, unseen population of millisecond pulsars. These are ancient pulsars spun up to incredible speeds by siphoning material from a companion star, and they emit steady beams of gamma rays. Thousands of them, too faint for Fermi to resolve individually, could blend together to create that smooth excess glow. Other explanations look to the past fury of Sagittarius, a star itself. Our central black hole is quiet now, but it may have had explosive feeding episodes in the past, accelerating particles to near light speed that could still be producing gamma rays as they interact with the surrounding medium. The debate is intense because the stakes are so high. Proving the signal is from dark matter would be a Nobel Prize-level discovery, fundamentally changing our understanding of particle physics and cosmology. Proving it is from pulsars would be a monumental achievement in astrophysics, revealing a hidden population of stellar remnants. As of now, the data refuses to settle the argument. More sensitive telescopes and advanced statistical analyses are chipping away at the problem, searching for the faint, telltale pinpricks of light within the glow that would betray the presence of pulsars. So far, no definitive cluster of point sources has been found to explain it all away. The silent fog at the center of our galaxy remains a luminous question mark. It is either a beacon from the dark sector of the universe or a testament to a stellar graveyard of unimaginable scale. Either answer reveals a cosmos far stranger than we knew. That luminous question mark at our galaxy's heart is a symptom of a deeper, more widespread cosmic disobedience. The true strangeness begins with a simple, universal law that governs our solar system perfectly, yet fails spectacularly across the vastness of a galaxy. Johannes Kepler, centuries ago, described how planets orbit the Sun. The closer a planet is to the gravitational source, the faster it must travel to avoid falling in. Mercury, the innermost planet, races around at nearly 50 kilometers per second. Distant, icy Neptune, by contrast, plods along at a leisurely 5. This is Kepler's law of orbital motion, and it works flawlessly here at home because almost all the mass, over 99% of it, is concentrated in the Sun at the center. For generations, astronomers assumed spiral galaxies would obey the same elegant rule. A galaxy's bright, central bulge contains most of its visible stars, its suns and gas clouds. Logic dictated that stars farther out in the faint spiral arms should orbit more slowly, just like Neptune. When Vera Rubin and others began measuring these stellar speeds in the 1970s, they expected to see those outer stars crawling. The data delivered a shock. The orbital speeds did not drop off. They remained high, flatlining across the entire galaxy. A star 60,000 light-years from the galactic center orbits just as fast as one only 20,000 light-years out. This graph of speed versus distance, called a rotation curve, was supposed to be a steep downhill slope. Instead, it was a flat line, a stubborn horizontal bar defying gravity's most basic expectations. This was the rotation curve problem, the first undeniable evidence that our universe was missing something monumental. If only the visible stars and gas were present, those outer stars would be flung into the intergalactic void by their own centrifugal force. They are moving far too fast for the gravity of the glowing matter to hold them. The only way a galaxy can have this flat rotation curve is if it is embedded within an immense, invisible sphere of mass, a dark matter halo that provides the extra gravitational glue. This halo is not part of the starry disk we see. It envelops it completely, its density increasing toward the center but extending far beyond the last visible star. The observation is so clean, so repeatable in galaxy after galaxy, that it forced a revolution in cosmology. Yet the sheer weirdness of the result has also inspired scientists to ask a radical question. What if we are not missing matter but misunderstanding gravity? This is the premise of modified Newtonian dynamics, or MUND, proposed by physicist Mordechai Milgrom in the 1980s. MUND suggests that Newton's law of gravity, while perfect for the high acceleration environment of our solar system, breaks down in the extremely weak acceleration regime at the edges of galaxies. In those dim outskirts, gravity might become slightly stronger than Newton predicts, just enough to hold onto those speeding stars without invoking any unseen particles. For a time, Mann provided an elegant alternative, successfully predicting the rotation curves of many galaxies with a single tweak to the equations. But cosmology is a web of interconnected evidence, and dark matter explains far more than just galaxy rotation. It is essential for explaining how galaxies clump together in the early universe, how giant clusters bend light, and how the cosmic microwave background shows its specific pattern. Mann, in its original form, struggles to account for all these observations without also adding some form of unseen mass, which begins to look suspiciously like dark matter under another name. The debate is far from settled, with new versions of modified gravity being tested against ever more precise data. This fundamental discrepancy, this flat line on a graph where a slope should be, remains one of the most direct and puzzling clues we have. It tells us that either the cosmos is filled with a ghostly substance that refuses to interact with light, or our understanding of gravity itself, a force we thought we mastered centuries ago, is incomplete on the largest scales. Both possibilities are equally profound, and both keep this silent rebellion of the stars at the very heart of modern astrophysics. That silent rebellion of the stars is a clue to a larger cosmic discord, one that now threatens to unravel our most fundamental model of reality. We call this the Hubble tension, and it is not a minor squabble, it is a full-blown crisis in cosmology. At its heart is a simple question with two contradictory answers. How fast is the universe expanding right now? The number that describes this rate is called the Hubble constant. For decades, astronomers have refined two supremely precise methods to measure it. The results should, by all rights, converge on a single, beautiful number. Instead, they are stubbornly, undeniably pulling apart. The first method builds a cosmic distance ladder, one careful rung at a time. Astronomers start with nearby stars whose distances we can measure directly through parallax, the tiny shift in their position as Earth orbits the Sun. They use these stars to calibrate the true brightness of Cepheid variable stars, which pulse at a rate directly tied to their luminosity. By finding Cepheids in more distant galaxies, they can determine those galaxies' distances. Then they use those galaxies to calibrate the ultimate cosmic beacons, Type 1, a supernova. These stellar explosions are so consistently bright they can be seen across billions of light years. By measuring how fast these galaxies, with their known distances, are moving away from us, scientists get a direct, local measurement of the universe's current expansion rate. This painstaking work, led by teams using the Hubble Space Telescope, yields a precise and confident number. The second method takes a completely different path, looking not at the present but deep into the infant universe. It uses the cosmic microwave background, the fossilized light from the Big Bang, as captured in exquisite detail by the European Space Agency's Planck satellite. This ancient snapshot shows the universe when it was only 380,000 years old, a hot, dense soup of particles. By analyzing the subtle patterns of hot and cold spots in this light, the seeds of all future galaxies, cosmologists can work backwards. They plug these patterns into our standard model of cosmology, which includes dark matter and dark energy, and calculate what the expansion rate must be today. This method is equally precise and supremely elegant, relying on the physics of the universe's first moments. Here is the problem. These two masterpieces of modern science disagree. The local distance ladder measurement says the universe is expanding faster today than the Planck measurement from the early universe predicts. The gap between them is now so large that the chance it's a simple statistical fluke or measurement error is less than 1 in a million. This isn't a blurry margin of error, it's a chasm. One of our most trusted pillars of cosmology has developed a crack. This tension forces an uncomfortable conclusion. Our standard cosmological model, the lambda-CDM model that has beautifully explained so much for decades, might be incomplete. The discrepancy suggests something is missing from the story of the universe's evolution. Perhaps dark energy is not a constant but a dynamic force that has changed strength over cosmic time, accelerating the expansion more recently than our models allow. Maybe dark matter possesses some unknown property, an interaction with itself or with light that alters the expansion history. Or, most radically, it could point to a flaw in our understanding of gravity itself, or to the existence of entirely new particles that filled the early cosmos and changed its trajectory. The Hubble tension is more than a technical disagreement. It is the universe presenting us with a paradox, two of our most trusted ways of seeing, one looking out at the present, one looking back to the dawn, are telling us different stories about the very fabric of reality. Solving it will require either a profound discovery in new physics or a humbling admission that we have misunderstood something fundamental in the ancient light we thought we knew so well. But the universe's building blocks are not always neatly labeled. In the glowing clouds of nebulae and the dusty cradles of newborn stars, astronomers detect a persistent, ghostly signature written in infrared light. These are the unidentified infrared bands, a set of mysterious emission lines that have flickered in our telescopes for decades, a chemical fingerprint we cannot quite match to any known substance on Earth. When starlight falls on cosmic dust clouds, the dust absorbs the energy and re-emits it, but not in a smooth rainbow. Instead, the infrared spectrum shows sharp, bright spikes at very specific wavelengths. It is as if you were listening to a symphony and heard a recurring, beautiful chord, but could not identify the instrument playing it. These bands are the chord. They are everywhere in planetary nebulae, in the space between stars, and even in other galaxies, telling us that whatever is producing them is a fundamental ingredient of the cosmos. The leading suspects are a class of large, hardy molecules known as polycyclic aromatic hydrocarbons. Picture the soot from a candle flame or the char on a piece of grilled food. That is essentially what PAHs are: flat, stable molecules made of rings of carbon atoms with hydrogen around the edges. They are tough, able to survive the harsh radiation of space, and when they are jostled by starlight, they vibrate in ways that should produce infrared emission at set frequencies. The problem is one of imperfect matching. The observed bands are close to what we'd expect from PAHs, but not a perfect fit. It is like having a key that almost turns the lock. The precise wavelengths are slightly off, and the relative strengths of the different bands don't align exactly with any PAH molecule we have studied in laboratories on Earth. This suggests the space-borne molecules are more complex, perhaps larger, more charged, or attached to other materials like tiny grains of silicate dust. Their significance, however, is monumental even in their anonymity. These unidentified bands are a strong sign that complex organic chemistry is not unique to our planet. It is a universal process. The very stuff that forms the base of soot on Earth is being manufactured in vast quantities in the clouds where stars and planets are born. These molecules are rich in carbon, the essential element for life as we know it. They could be raining down on young planets, seeding them with prebiotic material, the raw feedstock from which the chemistry of life might eventually arise. The Orion Nebula, a stellar nursery visible to the naked eye, is a prolific factory for these mysterious emissions. Everywhere we look, from the remnants of dead stars to the hearts of active galaxies, we see this same cryptic signature, implying a universal chemistry operating on a galactic scale. Pinpointing their exact identity remains one of astrochemistry's grandest challenges. The difficulty lies in the remote nature of the observation. We cannot scoop up a sample from a nebula light years away. We must rely on the precise language of light itself. Scientists work tirelessly in labs, zapping candidate molecules with lasers to see if their infrared fingerprints match the cosmic ones. They consider not just plain PAHs, but variations that are ionized or frozen in ice mantles or clinging to nanodiamonds. Each new possibility tweaks the theoretical spectrum. The mystery persists because space is a far more exotic laboratory than any we can build, with conditions of temperature, density, and radiation that are nearly impossible to replicate perfectly. These unidentified infrared bands are a humbling reminder. They tell us the universe is not only filled with the potential ingredients for life, but it is combining them in ways we are still learning to read, writing a complex chemical recipe in a light we are only beginning to decipher. This universal chemical recipe depends on the very fabric of space itself, a fabric that should impose a strict speed limit on the most violent particles in the cosmos. The Greisen-Zatsepin-Kuzmin limit, or GZK cutoff, is a fundamental rule born from the emptiness between galaxies. It states that ultra-high-energy cosmic rays, those single protons screaming across the universe, cannot travel immense intergalactic distances. Their journey is doomed by the cosmic microwave background, that faint sea of photons left over from the Big Bang that fills every cubic inch of space. For a proton traveling at over 99.9% the speed of light, these harmless microwave photons appear as a barrage of high-energy gamma rays. The proton smashes into them, creating new particles and, crucially, losing a huge chunk of its energy with each collision. Over distances greater than about 300 million light-years, this process should drain even the mightiest cosmic ray, imposing a hard ceiling on the energy we can possibly detect from faraway sources. It is a cosmic speed limit written into the oldest light there is, but like any good rule in this universe, it appears to have been broken. In October of 1991, an observatory in Utah detected a single particle that shattered all expectations. It carried an energy of about 300 exa-electronvolts. To put that in human terms, it packed the kinetic energy of a fast-pitched baseball into a single subatomic speck. Scientists, in stunned disbelief, named it the "Oh my God" particle. Its energy was so far beyond the GZK limit that it seemed impossible. It was as if a marble rolling across a long gravel road arrived at your feet, moving faster than a bullet. Since then, a handful of other similar events have been recorded, each one a profound anomaly. These detections present a stark and thrilling puzzle. If the GZK limit is correct, then these particles cannot have come from a distant, powerful source like an active galaxy billions of light years away. They would have run out of energy long before reaching us. This forces three equally radical possibilities. First, our understanding of particle physics at these extreme, unreachable energies could be fundamentally flawed. The interactions between protons and the cosmic microwave background might work differently than our theories predict, allowing these cosmic bullets to travel farther than we think. Second, these particles must be coming from extremely nearby sources within our own galactic neighborhood, perhaps within the Milky Way itself. But this creates another mystery because we see no known object nearby capable of being such an unimaginably powerful particle accelerator. What local engine could possibly pack such a punch? The third possibility is the most exotic. These are not protons at all. They could be an entirely new class of particle, one that does not interact with the cosmic microwave background in the same way. Some theories suggest they could be stable, massive particles predicted by supersymmetry, or even microscopic black holes produced in the early universe. Each detection of a super GZK particle is a direct challenge, a tiny crack in the foundation of high-energy physics. They are messengers that seem to carry an impossible passport, stamped from a journey they should not have been able to make. Whether they point to a flaw in our maps, a hidden monster in our galactic backyard, or a completely new form of matter, they prove that the universe's most fundamental laws are still being written and sometimes broken. Beyond the shattered speed limit of cosmic rays, a quieter boundary exists in our own cosmic backyard. Out past the orbit of Neptune, where sunlight is 1,000 times weaker than on Earth, lies a realm of ancient ice and rock known as the Kuiper Belt. This is the solar system's attic, a vast disk of frozen leftovers from the dawn of planet formation. For decades, astronomers have been cataloging its inhabitants, from dwarf planets like Pluto to countless smaller, icy worldlets. They expected a predictable distribution. As you move farther from the Sun, the number of these objects should gradually thin out like a crowd dispersing from a central point. But the universe, as always, had a surprise in store. The population does not fade gently into the dark. Instead, it hits a wall at a distance of about 50 astronomical units, roughly where Pluto orbits. The belt is bustling. Just a little farther out beyond that line, there is a sudden and dramatic emptiness. The number of detectable objects drops off a cliff. This is the Kuiper Belt cliff, a stark edge to our planetary system that no one predicted. It is as if you are walking through a dense forest that abruptly ends at a razor-straight line, with nothing but open plain beyond. Our models of solar system formation cannot easily explain such a sharp boundary. The primordial disk of dust and ice that swirled around our infant sun should have blended more smoothly into the interstellar void. So what carved this cliff? One of the most compelling and controversial theories points to the gravitational hand of a hidden giant. Astronomers studying the peculiar, clustered orbits of some extreme Kuiper Belt objects have proposed the existence of a ninth planet, a world perhaps 5 to 10 times the mass of Earth, orbiting hundreds of astronomical units from the Sun. This hypothetical planet 9, if it exists, could be the architect of the cliff. Its immense gravity over billions of years might have shepherded the orbits of smaller objects, clearing out a vast region beyond 50 astronomical units and sculpting the inner edge of a distant, sparse population. It is a fascinating idea, a hidden world shaping the structure of our solar system from the shadows, yet other scientists argue for a more ancient, fossilized explanation. They suggest this cliff might simply be the original outer edge of the Sun's planet-forming disk. Billions of years ago, our star was born in a cluster with many siblings. Perhaps a close pass by a neighboring infant star stripped away the outer material, leaving our protoplanetary disk neatly truncated. Or maybe the disk itself just ran out of building material at that specific distance, a frozen snapshot of the resources available when the planets were young. Each explanation carries profound implications. A planet 9 would be a monumental discovery, rewriting our solar system's family portrait. A primordial edge, however, would be a priceless fossil, preserving the exact conditions of our system's birth. For now, the cliff stands as a silent sentinel in the dark, a boundary marker whose meaning we are still struggling to read. It reminds us that even the familiar architecture of our home system holds deep and unresolved mysteries waiting just beyond the last known planet. That hidden boundary in our own solar system is a reminder of how much we have yet to learn about cosmic evolution, a lesson driven home with startling clarity by a familiar giant in our night sky. In late 2019, the constellation Orion, that iconic winter hunter, began to look strangely lopsided. Its brilliant right shoulder, the red supergiant star Betelgeuse, was fading. Week by week, its light dwindled, plunging from one of the top 10 brightest stars in the sky to a faint orange ember, dimming by over 60%. For astronomers and stargazers alike, it was a breathtaking, nerve-wracking spectacle. Betelgeuse is a star on borrowed time, a cosmic titan nearing the end of its life. Such a dramatic dimming sparked a thrilling, urgent question. Was this the final act? Were we about to witness with our own eyes a star explode in a supernova, an event not seen in our galaxy since Kepler's star in 1604? Telescopes across the globe and in space swiveled toward Orion. The Hubble Space Telescope, along with a fleet of ground-based observatories, captured the star in unprecedented detail, not just in visible light but in infrared and ultraviolet. They were looking for the telltale signs of a star in its death throws wild fluctuations in temperature, or the telltale neutrino burst that signals core collapse. Instead, they found something more subtle and in its own way more revealing. The data painted a compelling picture. Betelgeuse in its turbulent old age had coughed. The star had ejected a colossal plume of superheated gas from its southern hemisphere. As this material traveled away from the searing surface, it cooled rapidly, condensing into an enormous cloud of silicate dust, essentially cosmic soot. This dust cloud, drifting between Betelgeuse and Earth, acted like a vast temporary shade, blocking a significant portion of the star's light from our view. By early 2020, as the cloud dispersed, Betelgeuse returned to its normal brightness. The immediate panic was over. The supernova was not imminent. Yet in solving one mystery, astronomers uncovered a deeper one. The event was a stark, real-time lesson in the violent and poorly understood final chapters of a massive star's life. We had front-row seats to a dramatic episode of pre-supernova mass loss. Stars like Betelgeuse do not die quietly. In their final millennia, they become unstable, pulsating and heaving vast quantities of their own material into space in fits and starts. This ejected material forms the building blocks for future planets and life, but the mechanics of this process are chaotic and unpredictable. The great dimming of Betelgeuse showed us that these eruptions can be far more localized and dramatic than our models suggested. A single, giant belch of gas from a specific region on the star was enough to cloak its entire visible face from our perspective. It revealed gaps in our understanding of convection in these stellar giants, the behavior of their immense magnetic fields, and the precise timeline of their final decay. So while the star itself is safe for now, the event left a profound legacy. It transformed Betelgeuse from a distant point of light into a dynamic, studied laboratory. We now watch it with new eyes, knowing that its next dimming event could be another dust cloud, or it could, one day, be the real thing. The mystery solved was merely a prelude to the greater enigma of how these colossal stars truly spend their final days. Even the matter we understand is playing a cosmic game of hide and seek. We have spoken of the profound mysteries of dark matter and dark energy, which together make up 95% of the cosmos. But what about the remaining 5%? This is the ordinary stuff, the baryonic matter, made of protons and neutrons that constitute every star, every planet, and every one of us. It is the universe we can see and touch. Astonishingly, we cannot even find all of it. This is the missing baryon problem, and it reveals that our own kind of matter is far more elusive than we ever imagined. Cosmologists, using the precise blueprint of the cosmic microwave background, can calculate exactly how much ordinary matter should have been created in the Big Bang. They get a specific, reliable number, then they take a cosmic inventory. They add up all the glowing stars in all the galaxies, all the cold gas clouds, all the hot plasma within galaxy clusters. The sum is a disaster. It accounts for only about half of what the models demand. Billions upon billions of suns worth of ordinary matter has simply vanished from our ledgers. So where did it go? The leading suspect is not a distant place, but a diffuse and ghostly state. Theorists believe the missing baryons are not clumped into bright objects, but spread throughout the immense voids between galaxies in a tenuous, superheated web of gas. This is the warm-hot intergalactic medium, or WIM. Imagine the cosmic web of dark matter, the great scaffolding of the universe. Along the filaments of this web, ordinary matter is also drawn, but it is heated to temperatures between 100,000 and 10 million degrees by the gravitational shock of falling into these vast structures. At these temperatures, the gas is so energetic it does not form cool clouds or stars. It exists as a thin, ionized fog, glowing faintly in far ultraviolet and X-ray light. Detecting this WIM is one of observational astronomy's toughest challenges. It is like trying to see the faint, hot breath of someone standing a mile away on a foggy day. The gas is so diffuse that its signal is incredibly weak, and it is spread across such vast volumes of space that it blends into the background. Astronomers have had to become detectives looking for indirect signatures. One clever method uses distant quasars, the brilliant beacons powered by supermassive black holes. As the light from a quasar travels billions of light years to reach us, it passes through these intergalactic filaments. Atoms in the WIM, like oxygen and neon, absorb specific wavelengths of that brilliant light. By studying the quasar's spectrum, scientists can see the faint, telltale absorption lines, the chemical fingerprints of this ultra-hot gas, proving it exists and measuring its properties. Another approach is to look for the faint X-ray glow emitted by the WIM itself, a task requiring incredibly sensitive space telescopes. Recent years have brought promising confirmations. Observations have started to tally up more and more of this hard-to-see material, and the numbers are beginning to close the gap. It appears the missing baryons were not missing at all. They were just hiding in plain sight, woven into the universe's very architecture. Solving this puzzle does more than balance a cosmic ledger. It reveals the true nature of the cosmos. The bright galaxies and shining stars are merely the glittering jewels. The WIM is the hidden setting that holds them all, a vast, hot ocean of normal matter that forms the unseen backbone of everything we once thought we could see. The missing matter of the universe hides in a hot, invisible fog, but some mysteries announce themselves with impossible geometry. In 2019, astronomers surveying the sky with a powerful new radio telescope called ASCAP in Australia stumbled upon something that made no sense at all. They were looking for the faint radio whispers of distant galaxies. Instead, they found perfect ghosts. The data revealed 4 immense, crisp circles of radio emission hanging in the void. They were so perfectly circular, so symmetrical, that they looked like cosmic smoke rings or the ripples from a stone dropped into a pond of space. They named them odd radio circles, or ORCS, and they are one of the most baffling discoveries of the modern era. What makes ORCS so deeply strange is what they are not. They are completely invisible. Point an optical telescope, an infrared sensor, or an X-ray observatory at their coordinates, and you see nothing but empty space. They only reveal themselves in the specific wavelength of radio waves. It is as if you could hear the clear, resonant note of a bell ringing in a dark room, but when you turn on the light, the room is utterly empty. No bell, no striker, nothing. Their scale is almost incomprehensible. Each circle spans about 1 million light-years across. That is roughly 10 times the diameter of our entire Milky Way galaxy. These are structures on a galactic supercluster scale, yet they appear to be empty shells. Even more puzzling, most of them show no obvious central engine. There is no brilliant galaxy, no raging black hole at their heart to power such an enormous structure. One of the 4 circles does have a galaxy near its center, but that galaxy is quiet, ordinary, showing no signs of the apocalyptic violence you would expect to create a radio bubble of that size. So what could possibly carve such perfect, titanic rings into the fabric of the cosmos? Theorists have been racing to find an answer, and each leading idea pushes the limits of known astrophysics. The first theory points to a truly monstrous event, the merger of 2 supermassive black holes. When the central black holes of 2 colliding galaxies finally spiral together and unite, they release a tsunami of gravitational waves. This cataclysm could, in theory, send a spherical shockwave racing out through the intergalactic medium at nearly the speed of light, a wave that might light up in radio emission as it plows through tenuous gas. This could explain the perfect circularity and the lack of a central source. The event was a one-time blast that has now faded, leaving only the expanding shell. A second idea looks to a different kind of galactic violence, a starburst galaxy. This is a galaxy undergoing a frenzied, explosive period of star birth. The combined effect of countless supernova and stellar winds from newborn stars can drive a powerful, spherical outflow into intergalactic space. Perhaps we are seeing the relic of such an outflow, a fossilized bubble from a starburst that has long since quieted down. Yet even this requires an outflow of unprecedented power and scale to create a structure so large and so symmetrical. The most intriguing possibility is that ORCS represent an entirely new type of astronomical phenomenon, the remnant of a cataclysm we have never before witnessed. Could they be the throats of wormholes, the imprints of collisions in the early universe, or the scars from a kind of hyper-energy event we have no name for? The discovery is so fresh that the mystery is still wide open. With only a handful of these circles known, every new one found provides another clue. They are a reminder that even in an age of magnificent telescopes, the universe can still present us with forms of pure, elegant mystery that stop us in our tracks and demand we rethink what we know about the architecture of everything. These perfect, ghostly circles in the void are puzzles of cosmic geometry, but the final mystery on our list is one of pure information, a paradox that threatens to unravel physics itself. It begins with a stunning realization from Stephen Hawking. A black hole, that ultimate cosmic prison from which nothing escapes, is not entirely black. Hawking showed that due to quantum effects at the very edge of its event horizon, a black hole must slowly leak radiation. It glows ever so faintly with what we now call Hawking radiation. This glow has a terrifying implication. It carries energy away from the black hole, causing the monster to slowly lose mass, shrink, and over unimaginable eons evaporate completely. This was a triumph of theoretical physics, weaving quantum mechanics into the fabric of gravity, but it created a catastrophe. The Hawking radiation predicted by Hawking's original math is purely thermal. It is random noise like the hiss of static from a hot stove. It contains no details, no fingerprints, no record of what created the black hole in the first place. Whether you throw a library of encyclopedias, a star, or 100 elephants into a black hole, the radiation that eventually leaks out as it evaporates would be exactly the same, a featureless fuzz of particles. This is the black hole information paradox, and it is a direct assault on a sacred rule of quantum mechanics. Information cannot be destroyed. In our universe at the quantum level, everything is information. The spin of an electron, the type of a quark, the arrangement of atoms in a book, this is all data. Quantum mechanics insists this information is always preserved. It can be scrambled, hidden, or transformed, but it can never be erased from reality. If a black hole swallows a star and then evaporates into random thermal radiation, the unique information about that star is gone forever. It is as if you burned a complex, unique sculpture in a furnace, and all that remained was a pile of identical gray ash, with no way to reconstruct the original artwork. The paradox forces a brutal choice. Either Hawking was wrong, and information does escape black holes somehow, which breaks our understanding of gravity and space-time near the event horizon. Or quantum mechanics is wrong, and information can be destroyed, which shatters the foundation of all modern physics. Neither option is acceptable, so for decades, theorists have waged a fierce war of ideas to resolve the conflict. One of the most profound proposals is the holographic principle. It suggests that all the information about everything that falls into a black hole is not lost inside, but is encoded in a scrambled, two-dimensional form on the surface of the event horizon like a cosmic hologram. The three-dimensional interior we imagine is, in fact, a projection of this data on its boundary. When Hawking radiation escapes, it is not random. It slowly and chaotically reads this encoded data, leaking the information back out over the black hole's entire lifetime. Another, more violent idea is the firewall hypothesis. It proposes that instead of a smooth, empty space at the event horizon, there is a searing wall of ultra-high-energy particles. This firewall would instantly destroy anything crossing the horizon, but in doing so, it could preserve information by making the interior of the black hole fundamentally separate from the exterior universe. It is a drastic solution that many find unsettling, as it replaces one paradox with another. The debate rages because this is not just about black holes. It is about the fundamental compatibility of our two great theories of reality. General relativity, which governs the very large, paints black holes as smooth, predictable geometric objects. Quantum mechanics, which governs the very small, demands the preservation of information. Where they meet at the edge of a black hole, our understanding of reality breaks down. Solving the information paradox is the key to a deeper theory of quantum gravity, a theory of everything. It asks the most basic question of all. In a universe built from information, what happens when reality itself is swallowed by a hole in spacetime? From a single, unexplained radio signal to the ultimate paradox of information in a black hole, this journey has spanned the full spectrum of cosmic mystery. We have witnessed the patient, geometric artistry of dying stars and felt the phantom tug of dark matter on entire galaxies. We have tracked interstellar visitors with impossible shapes and stood before the stark, silent walls that define our own solar system. Each of these 25 phenomena, from the faint young sun that warmed our infant planet to the great attractor pulling us into the void, represents a frontier. They are not failures of our understanding, but its very fuel. Every unexplained rotation curve, every missing lithium atom, every ghostly circle in the radio sky is a beacon. It is a signal far clearer than any wow that our maps of reality are incomplete. These enigmas are the universe's way of questioning us, pushing human curiosity to look deeper, think harder, and build better tools. They remind us that the cosmos is not a static museum, but a dynamic, evolving puzzle, far stranger and more wonderful than our boldest fiction. So as you look up at the night sky, let these mysteries linger in your mind. Which one captured your imagination the most? Was it the perfect hexagon raging on Saturn, or the silent, all-pervading dominance of dark energy? Share your thoughts below. If you crave more journeys to the edges of understanding, be sure to subscribe. The universe is vast and its greatest secrets are still waiting. Keep looking up and never stop wondering.